Hello everyone, I'm Pablo Prieto from the University of Cantabria in Spain, and I will present you our work on a methodology for fast performance evaluation using heterogeneous multi-program workloads that we call SPECCast. Through these slides and the associated paper, we are presenting an improved performance evaluation methodology built on top of existing benchmarking tools. Performance evaluation through benchmarking is one of the keys in our field, and among all available tools, SPEC provides some of the most relevant performance suits, such is the case as the 2017 CPU version. One of the key aspects of SPEC CPU is the definition of different suits according to the performance metric selected, like latency or throughput. On one hand, SPEC speed focuses on execution time metric, running a single multi-thread copy of each workload, and is optimized for high-speed execution. In contrast, SPEC rate analyzes throughput metrics, running one copy of the same application per core. In our opinion, performance evaluation through SPEC rate suite presents some weaknesses that can be improved. First, the homogeneous configuration where every core in the processor runs the same software is far from being representative, where a mix of multiple different applications running simultaneously seems much more realistic. Second, this homogeneous configuration limits the number of available workloads to only 23, which is far from enough for statistical significance. For these reasons, many researchers, as we do in this work, stand for going heterogeneous as a solution of the problem cited. However, simply doing this uncovers new limitations that must be taken into account. For example, and using SPEC CPU 2017 as a source of representative applications, if you have 23 applications mixed in n cores, you will have 2 to the power of n possible workloads, which escalates quickly and means millions of workloads in a modern multi-core computer. In such case, it seems mandatory to use statistical tools to reduce the number of workloads needed to make an informed decision. But how many do we need? We perform a statistical analysis to answer this question. We launch one application per core and measure the average instructions per cycle and evaluate how many workload samples do we need to obtain a normal distribution. So we can use statistical tools and the results are statistically sound. It's important to notice that not every application ends at the same time, and we need to wait until the last one has ended to get correct results. To achieve that, we launch each application in an infinite loop, as can be seen in the figure, and using Linux perf tools, measure performance as the average instructions per cycle until the slowest application has completed 2 full executions. We present in this graph the normal distribution and the distributions obtained with the number of samples selected. As can be seen with 20 samples, the distribution vaguely follows the normal distribution, but with a high error. As the number of samples increases, the error goes down. And with hundreds of samples, you seem to get statistically sound results. But hundreds of samples means several days of execution. How do we reduce the computing time needed for such an amount of samples? Well, the solution that comes to mind is application sampling, which is widely used in performance evaluation, especially using simulation tools. For this work, we have followed an alternative approach to the runtime profiling methodology of well-known solutions such as Synchronous. In contrast, analyzing source code, we realize that most applications spend most of their execution time in a repetitive loop structure such as a while or a for statement. Studying this region of interest in detail, we have verified that the architectural behavior of each iteration of this loop is quite similar of the rest of the iterations. To illustrate this, we show in this slide the measured instructions per cycle in 100 millisecond intervals. And as can be seen, there is a repetitive pattern matching each iteration, and there is no substantial difference between any 2 iterations. And this is not an isolated effect, and if the same evaluation is performed for all the SPEC applications, similar results can be observed. In this figure, we represent in blue the behavior of the whole applications in instruction per cycle, level 1 data cache misses per 1,000 instructions, and branch miss predictions. The orange columns represents the arithmetic mean of iteration performance values, while the error bars shows the standard deviation. A small error bars points out that a significant degree of similarity between loops is present in most SPEC applications. Additionally, there is another significant result, which is the similarity between the average per iteration values and the results observed for the whole application execution. And this means that one or few iterations are representative of the whole application, being a suitable candidate as a standard sampling region. However, applications should execute the region of interest concurrently for the results to be meaningful. But the time each one requires to reach that point, the beginning of the region of interest, is different for each application. So we need to use some form of synchronization mechanism before making any measure. So we can go from this to this. So we can make sure the portion of the application we are measuring is the representative one, the region of interest. And these are the two keys of our solution that we call SPECCast, a methodology that uses sampling plus synchronous execution and performance monitoring unit-based profiling to get fast performance evaluation of heterogeneous multiprogrammed workloads. As mentioned in previous section, our sampling region selection will be based on the presence of a region of interest inside a loop-based control structure. This methodology requires source code annotation of the region of interest, and we will illustrate it through the sample in this slide. We follow a standard approach to find and label the region of interest. In first place, we profile the application, making use of Linux perf tools to generate a Flamegraph, such as the one in the figure. This graph shows a software stack indicating hot code paths, and in case of the figure, we observe that most of the execution time corresponds to the function labeled as priceout IMPL and primal BEA MPP. These functions are then located in source code, checking if they belong to any loop structure. If the loop is identified, code is annotated, and a preliminary evaluation is performed. The total execution time is compared to the time spent in the region of interest loop, and only if the region of interest represents at least 85% of total execution time, the application is considered valid for our methodology. To synchronize the region of interest of each application, we use a shared barrier. We use a POSIX thread barrier mapped to a POSIX shared memory object, and using previous code annotation, we then add a barrier wait call at the beginning of the region of interest of each SPEC application. A launcher program is responsible of initializing the barrier and launch each application selected, making sure each one runs in a different core using sketch set affinity. Once all the applications are synchronized, they execute the region of interest simultaneously. We added then utility to the methodology on not only being able to generate multiple heterogeneous workloads synchronized, but creating an evaluation tool. We include the PAPI Library in our launcher program to access hardware counters, so we are able to measure the behavior of the application executing. The SPECCast launcher attaches PAPI event list to each application and starts measuring as soon as all the processes reach the barrier. Using PAPI, we are not limited to just performance metric like execution time or instruction per cycle, but to any metric available through the performance monitoring unit, which includes catches, access and misses, branch predictor behavior, prefetch misses, etc. We could be able to obtain even a top-down analysis of each application running if the PMU allows it. Although we can measure a given number of region of interest loop for the evaluation, we decide to use time as not all the loops have the same length. But how much time do we need to run to get meaningful results? Well, we conduct an experiment where we run the same 1,500 workloads for different time periods of the region of interest. In the figure, we can see the 1 second measurement times. We measure the average instruction per cycle and compare the results with the average instruction per cycle of full application execution of the same workloads, as can be seen in the figure. Turns out that we need at least 10 seconds to get a statistically sound result. Less than that, and some applications do not execute even a single iteration of the region of interest. That means that with 10 seconds measurements, we are able to get 500 measures, 500 data, in less than 8 hours. And there are methods to reduce that time even more. So to put it into perspective, we need several days, less than a week, to get the same 500 samples with whole application execution. That means approximately 20 times faster. We have performed an exhaustive statistical validation process of our methodology that is thoroughly described in the paper. including a two-sample Kolmogorov Smirnov test for different sample sizes, obtaining p-values that confirms the similarity of SPECcast and full SPEC execution results. Once presented and validated, we will show some use cases that further validate and expose the benefits of the methodology. The first example is a measure of performance impact of the last level cache hardware prefetcher. We compare the results obtained with using SPEC rate from the SPEC CPU 2017, following the official procedure of running and reporting rules, and we compare that with SPECcast running 1000 workloads, which uses a similar amount of time as the time needed for SPEC rate complete evaluation. Although we know we can use 500 samples, which are enough, and can be obtained in half the amount of time. Curves in the figure represent the normal distribution of the results obtained with both methods, while bars represent the real histogram of the data. We can see how the normal distribution of the curve follows the SPECcast histogram really well, while that's not true for SPEC rate due to the low number of samples used. Figure shows how SPECcast provides a narrower distribution with lower variance and indicating an improvement of Prefetch usage of 18% with a 98% degree of confidence, while SPEC rate gives us a 15% improvement of using Prefetcher with a 75% degree of confidence. Well, then we conduct a similar experiment, this time comparing two different machines called Desktop, which is an Intel i5 with 4 cores, and one we call Server, which is an Intel Xeon Silver with 32 cores. We can observe how average values are close with both methodologies, and both gives us that Server is almost 5 times better than Desktop, which reinforces the idea that the SPECcast is a valid alternative methodology. But again, SPECcast significantly reduced the standard deviation, increasing the confidence level that Server machine is better than Desktop, being there is no significant overlapping areas. Unlike with SPEC rate, with an overlapping area, even with such different systems. Finally, simulation is pretty important in computing architecture, where relevant benchmarks are needed, and reducing the computational effort of simulation is critical, as simulation have a high computational cost. Many methods rely on sampling techniques, and SPECcast follows a similar approach, but it provides the possibility of executing heterogeneous workloads with synchronized execution of a meaningful region. SPECcast can be used with full system simulators like Gen 5, which is probably the most widely extended. We perform some experiments that are described in the paper, and we then take advantage of loop annotation to be able to execute one iteration of the region of interest, which significantly reduces the execution time needed, as can be seen in the figure, reaching from 1 to 3 orders of magnitude of computational cost reduction, depending on the application. As summary, we have presented our methodology, which wants to be a collaborative tool and is openly available at this GitHub URL. It's a tool that is currently under further development, and we have already extended to include more applications other than SPEC CPU 2017, which at this moment includes NAS parallel benchmark and parsec benchmarks, but we want to expand that even further. And additionally, we are including new metrics and studying the possibility of using checkpoints as a way to reduce even more the computing effort. Please feel free to use the tool and contact us to this email address with any doubts, suggestions, or interest. And thank you for your time, and I hope to see you in the Q&A session.